see that those short questions are not related to each other. This one is just this, but the previous one is completely something of a completely different topic, so they are not quite related to each other. Just a collection of like small questions, nothing more. So third one is this. So again, getting back to the true, false, or uncertain type. First write them, and then we talk about it. So there's the random variable W, and we do know that it takes two values, W1 and W2. First case happens with a probability of 40%, 0.4. And the other case, this random variable takes on second value, W2, happens with a probability of 0.6. Then the statement concludes the expected value of W1 is the same as 0.4 times W1 plus 0.6 times W2. So first say whether this statement is true, false, or maybe not certain, and back it up. Justify. True or false? True. True. Take a good look at on the left hand side. What is it? False. What's the expected value of W1? So there's a slight difference in this notation. That's uppercase. So capital W is a random variable, and we do know that the capital W takes on either small w1 or small w2. These are the numbers, and then that happens with different probability. First one 0.4, for the second one 0.6. So if you take a good look at on the left hand side of this equation, what's the expected value of small w1? Anybody? What's this? 5. Just a number. There's no probability. Same thing. It's just a number taken by this uppercase W, which is different from this small w1. E of w1 is just a w1. There's no probability because it's fixed. So this statement is clearly wrong. And if you write it in more, just say that it's false because expectation of w1 is just a w1 because that's just a number taken by this big W. So this one is a random variable. There's an uncertainty. There's a possibility that this value could be different, either W1 or W2. But this is just a number like a 3 or 5. And this is just another number, maybe 100 or million. And that occurs with different probabilities, 0.4 and 0.6. So if you want to make this statement correct, you have to replace this small w1 by this guy, big W. Then it's correct, but not this one. It's clearly wrong. So if the statement says expected value of big W and then says the rest, then of course that's true, but not this one. Now number 4. 3 more and then we go over to the next part. So again, true, false, or uncertain. Given the different statement, but setup is the same. W is defined as the same way in question 3, the previous one. Just the same way it was defined. So either for W1 or W1 or W2, but the first one occurs with a probability of 0.4. The second one occurs with a probability of 0.6. And now you turn to the variance of W, not the expected value. So it claims that the same W defined as in the previous question, if you compute the variance of W this time, the probability of first occurrence 0.4, and then the stuff inside is squared, is W1, the first value taken by this W, then expectation of W1, and 0.6, the probability for the other outcome, and that outcome is W2, and subtract the mean of W2, and then square. First say true, or false, or maybe not, maybe neither, and then explain why. So what is it? True or false? False. Why is it false? Something's wrong. What's wrong? Yeah, this is wrong. What should this one be? Yeah, the big W should be big W. Same as this one. This one's wrong. Clearly wrong. Should be big W, uppercase one. Because that should be a random variable. If you just go ahead and compute this quantity, what do you get? 0, obviously, because this is the same as W1. It's just a number. If you take the expectation of it, it's just the same thing. So W1 minus W1 is clearly 0. So you get the 0 for the first half. And for the same reason, second half is going to be the same as 0. So the sum of two zeros is still 0. So if you write it in the correct way, so clearly the statement is false, because if you compute it that way, variance is going to be 0. If you want to turn this one into something correct, you should say that E of W instead of just E of W1 or E of W2. For the midterm, people usually do well. Last 2 years, last year was slightly higher than that from 2 years back, but students scored above 75 on average out of 100. Last year was above 80. I'm talking about the average. Like 6 or 7 guys were aced it, got 100. So I'm not particularly concerned about the midterm, because history tells me that they've been doing well. The final, quite the opposite happened for a couple of reasons. The material that we covered after the midterm exam becomes a lot more hard compared to the first half. Then what happens on the student side, they get relaxed after their good performance on the midterm exam. Weather is getting better and better. There's a festivity in the middle of May. Students skip the classes. So hope they won't be repeated this time. But the midterm's concerned, and they've been doing pretty well. So yes, that there's no exception with this one as well. One more question like this one, and then we try something different. So number 5. So another false, true, false, uncertain type. It's this one. Same W again. So same W as defined in question 3. Now you try the expectation of e to the W, not just the W. Just a function of W, and then you take on that expectation. And then the statement says that it's 0.4 times 2 to W1, so that's W1, plus 0.6 times 2 to W2, which is the second possibility. Now do the same thing. First determine whether this is true or false, and then justify either way. Answer to the previous two, number 3 and number 4, was a false statement. So for some change, this one looks like this is true, but this is indeed true. Why is it true? Because of, there's a reason why this statement is true. Because of one of the propositions that we did in the past. Remember this one? Not just true because the other two first were wrong, but because of the proposition. PMF, probability mass function. Oh, by the way, midterm covers up until lecture note 6. 7 is not included. No continuous random variable stuff. So midterm, let me write. One through 6. 7 will be included by the final. So basically 1 through 6 for the midterm and 7 through 12 for the final. Well, actually final is cumulative, everything, 1 through 12. With a lot more weight and focus on the second half, between the 7 and 12. So there are 12 lecture notes in this class. So the statement says if you want to compute the expected value of some function of x, you don't have to get the PDF of this function of x. You still get to use the PDF of x because of this proposition. And that's exactly the application of this statement on the board. So 0.4 and 0.6 is the probability mass function of w, not the PMF of this e to the w. It's still good to use because of this proposition. So if you use the PMF of w instead, first half of this expectation is that probability, and then the value that this function takes on, which is 2 to the w1. And the second half should be the other probability of the second w, which is w2, and then function of that value, which is 2 to the w2. So exactly the application of this proposition given here. You have something similar to this one in the continuous random variables case, but that one is going to be covered by the midterm. So no calculus stuff, no integration. Well, even for the final, there's no integration. No calculus is required. So the solution states this. So the statement is obviously true because of this proposition. So each one of these short questions is worth 5 points. So if you both the answer and the way you justify are correct, and you of course get 5. To say that your answer is wrong, but your explanation makes some sense, could be either 3 or 4, depending on how you justified it. But you clearly state the correct answer, true, but then you don't say anything else. You just stop there. So say that your answer just is true, and period. And your point for this one is obviously maybe 1 point out of 5, because you at least get the answer correct. But no more than 1. Because certainly this part is a lot more important. You have to say something more. Don't just say true or false and expect me to give you all the credit. One last question for the part 1, and then we move over. And this one, I first tried this type of question this class for 2 years back. One person got it, all the rest somehow didn't get it correct. It's this one. Something about Brownian random variable. It's no true, false, or uncertain type. It's just a computation. But once you get the idea, answer is very clear. So there's the messy appearing, but indeed not very messy, function of x. First you get number 300, and times x to the same number, 300. Subtract now 500 times, and x to the same number again, 500. And you're supposed to take the expectation of the whole function. So first, get this one. stuff inside the bracket, and then you take the expectation of everything in here. You're supposed to compute this value. And here x is assumed to be Bernoulli. You all know what Bernoulli is. Either 0 or 1, and then success probability is a 1/4. So which means that this x becomes 1 with this probability, otherwise it's just a 0. So that's Bernoulli. So how do you compute it? And what do you get if you compute it correct? Think about it like 1 minute. Let's compare. The reason why I ask you to think about it is because nobody's going to help you on the exam. You have to think yourself. So practice it. If the x is not a Bernoulli random variable, this computation is indeed messy. But it's greatly simplified only because this is a Bernoulli. X is either 0 or 1 with this known probability. X becomes 1 with this 25% chance, and X becomes 0 with the other 75% chance. So that's why the computation is rather straightforward. So the way to get it, first state this proposition, if you can. Because of this proposition, you don't have to know the PMF of this entire function. This is a function of x, one function of x. So in principle, if you want to compute the expected value of certain function of x, you first have to obtain the PMF of that function. But because of this proposition, you still get to use the probability mass function of x, which is this with the x equals 1, and the other 3/4 with x equals 0. So the computation simplified a great deal. So the correct answer should be this one. So given the fact that x takes on 1 with the probability p, just call that p for now. Success probability, which is known to be a quarter in this case, and 0 with the other probability, which is 1 minus p. And by the application of the proposition, expectation of the whole function is nothing but the value taken by that function, either this or that, but then the same PMF. The PMF, the same as that for x, can be used for computing this expected value. So if you compute this one, the whole second half disappears because this is nothing but 0. But then the first half, the power is high, but the base is just a 1, so it doesn't matter, it's still 1. So whether you raise it to the power of 300 or 3 million, just still 1. So this is 1, and that is 1. So difference between these two is just negative 200 times p, and p is known to be 1/4. So the final answer should be negative 50. Again, something like this, but not exactly the same, will be on your exam. Could be Bernoulli, but could be binomial, or something simple. And don't forget to bring a calculator. So you are allowed to use a calculator, but that shouldn't be your smartphone. No internet access is allowed during the exam. And this is complete closed book because the formulas will be given by the second page of the exam. So first page is just a front cover. You just put your name down, and then there's a score sheet. And the second page, there's a bunch of formulas, and the actual exam starts from page 3. Anything so far? No? Alright. Let's go to the second part. Conditional probability. Let's write down the question first and then let's talk. So for this type, there's a one consistent theme. And that theme in this case is conditional probability. So the first sub-question A and then the what follows, which is part B, they're related to each other. So the situation is that there's a couple and they have 2 children already. And probability of having a boyfriend in their case is about a third. Why third is just an assumption. And each birthday is supposed to be independent of the other, and assume further that they don't have any twins. And given all that, we want to compute the following conditional probability, assuming that the oldest one, first child is a girl, and what is the probability that both of them are actually girls? So they're related to each other. First, assuming that this is the case, has already occurred, what are the chances that the second one is also a girl? The same thing can be put in a slightly different way. You can say that, assume that their first child is a girl, and then what is the probability that the second one is also a girl is the same thing. So either way, you have to compute this conditional probability. So conditional probability, first state the definition. P of A given B is nothing more the ratio of probability of A intersection B to probability of B, which is conditioning part. So if you do it, you get this. So first state the definition. Given that the oldest one, the first one is a girl, you want to go for the probability that second one is also a girl. But according to the definition of this conditional probability, that's nothing more than this just a ratio. Both of the conditioning part and conditioned part, both of them are girls. And the first one is a girl, divided by probability for the conditioning part. The first one is a girl. But then the key part is to seeing the fact that intersection of these two different events. So and is another notation for intersection. I mean cap, this one. So the intersection of these two is obviously both of them are girls. Because the first part make certain that the second is also true, but not the other way. So first implies the second, but second one doesn't imply the first. That's why the intersection is just the first. What I'm saying is the first event implies the second, but second doesn't imply first. So that's a smaller set. So intersection must be this one. But then you're only left with the computing or figuring out two different probabilities. First one is at the top. Both of them are girls. So that's 2/3 times 2/3. Why you have to multiply them? Why do you multiply? So both of them girls means the first one is a girl. And the second one is also a girl. But why do we multiply? Basically want the probability of A and B, right? So that's what this, both of them are girls. But then you assume that each birth is independent. So independence ensures that product of each probability is nothing but the probability of the intersection. So it's because of this part, this assumption. Independence among those different birds, making sure that this probability is the same thing as probability that the first one is a girl and the probability the second one is a girl. And that's nothing but the product of each probability. And bottom one is obvious. Oldest one is a girl is 2/3. So if you do this one of these 2/3 at the top is going to cancel by the what's in the bottom. So you're left with the first 2/3. Your final answer. Similarly, you can think about the second case. So same situation, you switch to the different probability. Now the conditioning part changes, assuming that at least one of them is a girl. Maybe both, maybe just the first or the second, but at least one of them should be a girl. You don't allow that both of them are actually boys. So assuming that this is already occurred, what is the probability? Actually the second one is also maybe the first. Both of them are actually girls. So it's a conditional, but different conditional from the first. How do you go for this one? Same as before. Start from the definition. Conditional. So a bit longer. But the same line of logic, reasoning can be applied to get to the correct answer. So first write out conditional probability, assuming that at least one of them is a girl. You want to compute the probability that both of them are actually girls. Then using the definition of this conditional probability, P of A given B is defined to be a ratio, P of A and B, so there's an and. Not or, that's the cap. So here that I write the and because that's the word. But this A and B, or A intersection B. And at the bottom, of course, you have to put the probability for the conditioning part. By the way, 2 people in this section were caught during the quiz by cheating. So if you ever do the same thing again, it's automatic F. So don't do it. Okay? I'm just telling you in advance. Pretty sure it won't happen again, but just in case. So the intersection of the both of them are girls and at least one of them is a girl. Obviously the both of them are girls because this is stronger condition. First one necessarily implies that at least one of them is a girl, but not the other way. The fact that at least one of them is a girl doesn't necessarily mean that both of them are girls. Could be one of them could be actually a boy. So intersection of these two, it's a stronger condition, which is the first one. And then the probability for the first, it's easy to figure out, 2/3 and 2/3 because of that independence again. But then the one at the bottom, you can divide it into 3 different cases. First one is a boy, second one is a girl, and the other way. And when a third case is both of them are girls. But the simpler way is first think about its negation, the complement. So complement of this one is both of them are boys. So that's this. So what I'm saying is computing this probability, same thing as first to compute its complement. And complement of this one is obviously probability such that both of them are boys. And that's this. And if you take the complement of that one again, and that becomes the original set, which is this one. So by first figuring out the probability that both of them are boys, which is 1/3 times 1/3, and the negation of that, which means they have to subtract that product from 1, and that will give you the correct probability for this bottom one. At least one of them is a girl. Or you can just go for the direct case. Count how many situations such that at least one of them is a girl. Obviously three of them. First one is a boy, second one is a girl, or the opposite case. First one is a girl, second one is a boy, and third one is both of them are girls. So figure out the probability for each one of these three and then add them up. That's going to give you the same answer as computing the answer for the second probability as it's given by the suggested solution. It doesn't matter which way you do it. As long as you get the answer correct, you still get the same answer back. Okay. One last one for today is the Bayes theorem, which is the hardest one among today's. Okay. Bayes theorem. Definitely will be on the midterm. Not just will be on the midterm, it's nearly 50%. Half of your exam is about this Bayes theorem. There will be 3 different questions about Bayes theorem. So if you don't get the Bayes theorem, your maximum score will be 50 out of 100. Half is gone basically. So practice it now. And of course, the Bayes theorem itself will be given. So don't try to memorize that formula. Over here, it's not given because it's a review. You have access to those notes and books and internet. But during the exam, the exact theorem stated by Bayes theorem will be given by the exam on the second page. So you just need to take a look at it and apply it. It's a bit lengthy. So none of those questions about the Bayes theorem is equation based. It's just something like this one. Explain the situation in words. You have to decode that first. Clearly, carefully read the statement and decode it into those formulas. No symbols, no number, or numbers will be given. No equations will be given by the exact question itself. It's just a description of certain situation. Now there's some criminal investigation going on. So the situation is the following. There's some case, criminal case, and then the inspectors are doing investigation to get the criminal who actually committed that crime. And there is one suspect. And then this inspector in charge is only about 50% convinced that this suspect is guilty. You know what suspect is? Someone who's believed to committed that crime, but it's not certain. Maybe he didn't. Maybe he did. So that's a suspect. So the cops first get those suspects and do the investigation. If there's enough evidence, this guy will be brought to trial, and judge will decide whether he should be convicted or not. So he's just a suspect at this stage. They're in the middle of collecting those evidences to make the case stronger. So he's only about 50% convinced that this guy indeed committed that crime. And the other 50%, he actually didn't. He's innocent. Now in the middle of collecting more pieces of evidence, information, pointing out that this guy indeed committed a crime, a new piece of evidence popped up, and then the criminal is left-handed. Uses his left hand, or simply lefty, same thing. So that's about the criminal, the guy who actually committed a crime. So this suspect may be left-handed, maybe not a left-handed. We don't know. But we do know that the criminal, the actual guy who committed that crime, is left-handed. Further, more information is given 30% of the entire population is left-handed in this society. And now the real question is how certain guilty of this suspect the inspector should be now with this new given piece of information that if indeed the suspect is left-handed. So he checked out whether the suspect, not the actual criminal, is left-handed or not. Assume that he is indeed a left-handed. But then what are the chances that he is the guy, the one who actually committed this crime? That's what's being asked. So there's a crime. The investigators are cracking down on one guy who's a suspect. He maybe did the crime or he maybe did not. Only about 50% chances at this stage. But new evidence popped up. The guy who actually committed the crime is left-handed. But then assuming that the suspect is indeed left-handed, what are the chances that this guy is actually guilty? Obviously, this is the case of Bayes' theorem. Think about like a minute or two. How are you going to go for this one? And then let's talk about. So since this example is being used here, will not be on your exam. But if you know how to handle something like this one, hopefully it will give you more options. Think about when you actually get to take on yours next Tuesday. There will be three questions like this one. Question A, B, and C, not related to each other, but there's the difference in the difficulty level. C is the hardest. Nobody got it last year. Almost everybody got A. About half of the class got B. So there's a change in the level of difficulty. But then like question A, B, and C all about Bayes' theorem, which is roughly 50% of your midterm exam. So where would you start? Always the first step in dealing with the questions regarding Bayes' theorem is define some random variable first. Yeah, define some random variable. Here, obviously 2 should be good candidates. What are those 2? That should be the first one. Name G, and then define it to be the event such that the suspect is indeed committed that crime, is guilty. The second one would be he is left-handed. Define G to be the event that the suspect is indeed guilty. And second event, LH, the suspect is left-handed. Left-handed. Now how would you compute this probability using these 2 symbols, G and LH? What do you want to get here? What do you want to get? What's the probability that you ultimately want to get here? conditional probability, of course, because this is a base theorem. Well, what should be in here? Left-handed. And here should be G. So now that everything is set up, I name the two events and then express the final answer that we try to get using those events. And just apply the base theorem to figure the answer out. Think about it yourself, like 1 or 2 minutes, and then we can discuss. Don't just think about something else. Think about this question. For Bayes' theorem, there's no more practice questions, just this one. So you better, practice now. And then, for other topics, I'll bring more examples tomorrow, but nothing, no more examples about this Bayes' theorem. That's why I'm asking you to imagine how it goes for this one. If you have forgotten the Bayes' theorem, check your reference, either lecture notes or some other sources. Because writing down the solution only take a minute. Still have like 5 more minutes to go. So plenty of time to think about it. Think about it like a minute or two, and then let's discuss what should be the correct answer for this. So stage is set up. 2 important events are defined. G to be the event that the criminal suspect is indeed a criminal. LH is defined to be the event that the suspect is left-handed. Using these 2 events, the probability that we try to get in this question is the conditional, assuming that LH, the suspect is indeed left-handed. What are the chances that he indeed committed a crime? And you want to use the Bayes' theorem to figure the answer out. The grading will be done by the TA because I'm not here, so she'll be proctoring the midterm. I will handle the official solutions the day before I leave. She'll finish the grading by the time I'm back. So the next class that we meet is, other than tomorrow's, that's May 11th? Is it? May 11th, I think. The Monday, second Monday of May. Once I get back those graded midterms, I'll quickly go through them, whether the grading was done okay. So I'm 100% sure that when I come back on May 12th, I'll come back with a graded midterm and score distributions and your tentative course grade, and you'll get it back. All the exams, graded exams and quizzes will be written in this class. And the official solutions will be posted on the class website. So everything is revealed. 3rd quiz is graded over the weekend, and then I'll bring them back tomorrow. It's in the hand of the TA now, but since we meet at 9 in the morning, I didn't have time to see her. She's supposed to return those graded quiz 3 sometime this afternoon, so I'll come back here tomorrow with your graded quiz 3. Solutions are already posted, I think. So you have 3 homeworks with the solutions and 3 quizzes for both sections with posted solutions, and plus the review questions for today and tomorrow. There's plenty of examples, exercises that you can practice on. So solution should be rather straightforward actually for this one. It's just this The P of G given LH, strict application of Bayes theorem says that's indeed this rather complicated ratio on the right hand side. Your job is to figure out what are the numbers, each one of these either conditional or unconditional probabilities. For the first condition on the right, the numerator, which is probability of LH given G, that's obviously 1. Why is it 1? Because it's known. New piece of evidence says that the true criminal is left-handed. So if we know that the suspect is indeed a criminal, he's guilty, he must be left-handed. And that's a certainty. So there should be probability 1. And P of G is given on the outset of the question. That's a 50% chances, so that's a 0.5. An interesting one is this one. Given the fact that he's not guilty, he actually didn't commit a crime, what are the chances that this guy, suspect, is left-handed? That's 30%. So this number will be used, should be used in there. For all non-criminal innocent citizens out there, about 30% of them are left-handed, so that should be the probability for this condition. That's the only rather tricky part. Rest of them is just straightforward. P of G complement, that's a 1 minus P of G, still same at 0.5 because P of G is 0.5. If you just compute these 6 different numbers, compute them correctly, you get probability 0.77, which is pretty high. Okay, so I would say write this one. So that there's 3 questions about Bayes theorem A, B, and C. Something between A and B in terms of the difficulty. So there are 3 questions on your exam about Bayes theorem. This one is slightly harder than the first one, but the weaker and easier than the second. But there's 2 more questions, second and the third one, which is supposed to be harder than this. So practice more on the Bayes theorem. Questions about anything else that we did today or anything else in general? Okay. Come back and tomorrow and let's continue.